using the microphone this time. Here we go. So, final lab exercise. DC motor PID position control. The objectives are to implement a position control system for an inertia-dominated load, explore appropriate path planning, and integrate the use of a standard MATLAB design tool into the application development system. So that's what we'll be doing in this lab. A lot of similarities to the previous two, like I said, but some new stuff. So in this exercise, a closed-loop position control system for the DC motor will be developed. The physical system is identical to that of lab exercise 7, as shown in figure B.14. So same schematic as before. Yeah. A MATLAB tool will be used to design an appropriate proportional integral derivative, or PID, controller, like the one shown in figure B15, which is here. So we have our motor system here. We have our control that we're going to be applying to the motor system, and take that output, feed it back to the PID controller, compared to our reference position this time instead of velocity, which we were doing velocity control before. So our reference is not a velocity, but now a position. And then we put our control output back to the motor. So that's our control scheme. Yeah. So later you evaluate the controller performance for a time-varying position reference path, so xref as a function of time. So we're going to move xref around. So we're going to say, like, go to 30 degrees position, go to 45 degrees position, hold it there for this long, go there. So go to all these different positions and evaluate how it performs that position control. So obviously when you tell it to go to 30 degrees, when it's not at 30 degrees already, it's going to take some finite amount of time to make it there. It might overshoot, oscillate. So we have control of those dynamic characteristics. It might have some steady state error. So we'll be able to investigate those in this lab. So it builds on past work that we've done. Program is structurally similar to that of lab exercise 7, and many of its components are reused. So path planning is probably the one of the newer aspects of this lab. So a common task for a positioning system is to start from a stationary position, move to a new location, and then stop. Of course, one way to do this is to apply an appropriate size step to the reference input of the position control system. So what you can do is the command can go from, say, your command was 0 degrees, and then suddenly you can make your command be 30 degrees if you want it to be 30 degrees. And then your actual system is going to respond however it responds, right? So this is something that when we were doing our lab 6, we saw this.
Overshoot.
Yeah, overshoot
And then come back down, overshoot again. And then
yeah. So this is yeah. However, depending on the system bandwidth, a sufficiently large step may require torques, which correspond to currents, electrical currents, and or velocities, which correspond to electrical voltages, that exceed the motor driver capabilities. Almost certainly it will do that if you do a sudden step in your reference. In addition, the dynamic characteristics, for example, rise time and overshoot, may be inconsistent with the application requirements. So the fact that we can't deliver, so like say we need to have like 5 times the torque at this moment is what our controller is computing than what we actually have, there are going to be issues that arise from that. So the main issue, so there are a few. So first off, we're going to saturate, right? So we don't always want to do that. We don't always want to have our control effort saturate. Sometimes it's okay, and we recognize that occasionally our controller will saturate. Not a big deal. But if you have that be the case, then when you modeled your controller design, when you were designing your controller and you were designing it for a specific rise time and settling time and all that, if in your simulation you didn't take into account that saturation, then the actual performance won't be the same. So you can do that. You can take into account the saturation of your control effort in your simulation, but it's harder to do that. It's essentially, it's a nonlinear process, right? Because you have your input torque or your input current or whatever suddenly gets clipped instead of going up higher than 7.5 volts. For instance, it would go up to your simulation would assume it was going up to 10 volts, which it can't do in reality. So your performance design is not going to be reflected unless you've gone through the process of saturating in simulation as well. It can also give rise to other issues too, like if you are flowing full current, say, through your motor. Oftentimes we can't do that for very long. We can do that for a short period of time, but if you do it for very long, it might melt the windings, and that would be very bad. It would ruin the motor. So that would be something you would try to avoid, and when you saturate, you're in more danger of that sort of thing happening. If you saturate for too long, then usually that would melt down the motor windings and break your motor. So we often we prefer not to saturate if we can avoid it. One remedy is to use a form of truncated ramp instead of the step reference input. So instead of saying, let's go from 0, and now I will sort of instantaneously change that from 0 to 30, my command, I'm going to more smoothly change my commanded position, and then the response will look however it looks. Probably lags behind and overshoots still. But when you have a smooth curve as the command, and don't just change it instantly, then you will be more likely to avoid this issue. So we are going to learn one way that's pretty nice to construct position control path planning. So instead of just saying, okay, I want to go from here, this command is, however that step input makes the system behave. I'm going to do it smoothly. I'm going to transition it smoothly. How do I define that smooth transition? What function do I use? And that's what we're going to do now. We're going to construct that. Is there like an optimal choice given some requirements? And the answer is yes. So depending on what your design requirements are, you might say want to keep your maximum velocity low, or you might want to keep your max acceleration low. And there are going to be trade-offs there. So the way that we'll learn to construct it, you can make choices based on design requirements. So this is one way to do it. Not the only way. You can come up with functions that are not like this too. But suppose that we wish to reposition a mass-dominated load by X max as rapidly as possible. subject to limitations on the maximum acceleration, Amax, and maximum velocity, Vmax, while avoiding discontinuities in the position slope. So these are all of these statements have been restricting which functions we're going to consider. They go from 0 to 30, right? Or from position 1 to position 2, or as this graph up here, which we'll be looking at in a moment, from displacement 0 to displacement x max. So how do we draw this function? We could draw it, any way we wanted. We could draw it like that. We could draw it like this. It could be, we could use a part of a sinusoid, use a tanh function. There's a whole lot of different functions you can use that would do this. So what's the best one? And this is one way to go about choosing it. So the motion has been divided into 3 sections: acceleration, constant velocity, and deceleration. So what I want to actually, I think it's probably better than reading through the text on this. I think we'll just look at this graph for a minute in detail. So we have our 3 time regions. So time is to the right here, so starts at 0. There's this initial time where we're speeding up, and then we have a constant speed region, and then we have a deceleration region. So you can make arguments for the shape that you could make acceleration, but if you're worried about a maximum acceleration, then it turns out that the optimal choice is a constant acceleration. If, say, you have a maximum of 15 meters per second squared, and you want to have this change in position happen as quickly as possible without over accelerating, maybe 15 is your max, then it turns out that having constant acceleration and then constant deceleration is the optimal way to go. Your Amax defines the height here and then the anti-height here, so negative Amax down here, and then 0 acceleration in the middle. So you're saying speed up, accelerate, and then keep it a constant velocity, and then decelerate. So the velocity is going to ramp up, and then it's going to stay constant, and then it's going to ramp down. Notice that these are constants. You integrate once to get velocity, and you get linear, and you integrate once to get position. So you integrate a second time to get position. So these curves are quadratic curves. And in this region, actually, this ends up being just linear, right? This is a constant, so. Quadratic, linear, quadratic. And it's smooth, right? So it's differentiable on the whole thing, which is nice. So we like this. This is a pretty nice curve. And it kind of accords with what we would think to be a smooth transition, right? Sort of S-shaped curve, smooth transition. If you are interested to make this happen in as short a time as possible, you would want to get rid of this no acceleration or deceleration region, okay? Because in this region, you're going at a constant velocity. You could be speeding up still, and then you could switch over to decelerating. So you could have this middle region squished to 0, right? You could move these guys in so that you're accelerating and then you're decelerating. But sometimes, so the trade-off, though, is that you're going to end up with a maximum velocity that's higher, right? Because it'll continue to go higher to this peak velocity, and then it'll be decelerating after all that. So if you have a velocity max that you care about, then you can't necessarily accelerate and decelerate the whole time. So there's sort of trade-offs here, and you can trade off between accelerating, max velocity, and the amount of time that it takes you. So setting it up this way is nice because actually working out the function is some trouble. But don't worry, you don't have to do it yourself. This function's given to you. But understanding how it works and why it works is important because it's a really common thing to want to do, to go from one position to another position. And doing it smoothly without saturation is a nice way to go about doing it. So this problem shows up a lot. In fact, so you guys remember the catcher bot that we did? That one was a problem that was very much like this, except we were trying to intercept a cell phone. That was what we were using as our test thing to drop. So you drop a cell phone, we would need to meet it at the right velocity. So meet it at a position and a velocity matching. And then decelerate as quickly as possible because we didn't have very much distance. So we wanted to be as optimal as possible. We wanted to move this position to the right height, and it had to reach that height right as it was hitting the same velocity, and then immediately start decelerating because it only had like this far to go. So it had to like catch it and stop. So it was a really hard problem, and they almost made it work. They did actually get it to catch cell phones without like it bouncing off or anything, so that was cool. But it didn't quite match the speed. You could tell there was a little bit of difference in speed. Mostly it was limited by the hardware that we had. The belt started slipping. We couldn't put enough tension on the belt to have it not slip because we had to put so much torque. But anyways, it was really fun. But this is a problem that's pretty common though. Like if you want to position something and have limitations on the acceleration you want or the max velocity that you want. Okay. So in this lab exercise, you will use a C function, sramps, that implements this time-varying displacement as the control system reference input. The function can link any number of ramp segments in succession, including specified dwell times at the end of each segment. So what you can do is you can have this thing go from one location to another location to another location, and sramps is set up to do that, and it'll dwell at each position for a certain amount of time. So at the end, when you test this, we're gonna give sramps like, I don't remember how many, 6 or something like that, 6, 7 different positions, and how long I should stay at those positions. And so when you guys are testing, it's going to go through, it's gonna turn left like a certain number of times and then stop at a position. It's gonna turn right a certain number of times and stop, and hold it there for a certain amount of time, and then go the other way and stop, the other way and stop. So that's the sort of protocol we're going through. And we're going to use this sramps function, which you don't have to write, to do that. Instead of, what you could also do is to just simply say, oh, my command is this now, and now I want the command to do something else instantly. You just change it, from one time step to the next time step. But then you're going to saturate for a while. Yeah.
So is the dwell time going to depend on how fast the motor gets there?
No, it will. So it's based on the SRAMP time it takes the SRAMP to go from one to the other. I don't think it takes into account the settling time. So what it's going to do is it's going to ramp up the command, which, so I'll draw in black, so that the command will be, say, going along here, and then we'll go through an SRAMP to a new position command. And what'll happen to your response will be that it'll probably be following this, and then it'll lag behind this a little bit, and it'll probably overshoot it and whatever. So your actual position will do that, but then your command is going to dwell there for this amount of time, and then however long you say, which there's a given protocol, and then it'll go to the other position, say you S-ramp to the next position, and then you dwell there, etc. So
So dwelling time does not depend on the way it moved before.
right, it's really just it's an amount of time that it's going to dwell at that command. So yeah. So it isn't necessarily waiting for your system to get there before it starts the clock on the dwell. The dwell clock starts as soon as the S ramp is done. As soon as the S finishes, it'll start the next thing. It'll start your dwell time clock, and then it'll start the next S ramp when that finishes. Okay, so for this exercise, you'll write 2 MATLAB scripts. One to design your PID controller, and the other to compare its performance to an analytical model. Specifically, the first script will design a PID-F controller, we'll talk about the F in a moment, controller using the MATLAB control system toolbox function PID tune. So the PID tune function, I'm going to have a little lecture on how to use this, but it is essentially does the selection of your PID gains for you. So proportional gain, your integral gain, your derivative gain. And then it has this option for adding in a filter using this PID-F scheme for a PID controller. So the filter, like I mentioned before, is going to filter out the high frequency noise for you. This is a low pass filter that will minimize the sensitivity of the controller to error noise, which is a problem for a derivative control system. So this compensator should be designed to track the reference input and to have control bandwidth of 8 hertz. So we'll talk more about that. That's the gets into the filter design. A PID-F controller improves noise immunity of a PID controller by limiting the high frequency response of the derivative term. Check your controller design by plotting the closed loop step response using the plant parameters from lab exercise 7. So it's the same plant, right? So we can use the code we used before to simulate a step response for the same plant, right? We have to alter the controller in our simulation, but then we can do a step response for our position control instead of for our velocity control, which we were doing before. So this is good, right? This is like the whole package. We're putting together a controller, and then we're going to simulate what we think it should do, and then we're going to actually implement that controller, and we're going to measure what it actually does, and we're going to see how we did. I mean, this is all of it. This is, you completely not only can predict things, but you can make things do what you want and predict how what you're doing will affect the system. Pretty cool. The script should convert the continuous time transfer function. So this is the script you're going to write, the first MATLAB script. Convert the continuous time transfer function to a discrete time transfer function. So C2D is what gives you a discrete transfer function from a continuous transfer function. TF is something that defines a transfer function. TF data will give you information about your transfer function. And then if you do a sample time, when you go C2D, you have to give it a sample time. So we're going to use 5 or 0.5 milliseconds again. And then use TF to SOS. So this is so transfer function 2 second order sections. This is what we did before as well, right? Well, I told you guys that this is what we did before, but you guys didn't necessarily do this before. So I will try to help you with this part too. So the idea is, remember we're using this biquad method, so we have to take the transfer function and convert it into a biquad, so a bunch of second order ones that are concatenated. So that's this TF2SOS function, gives us that. And then finally, and this is the, so from, everything from here to here is all built-in MATLAB stuff, right? But then we're going to use the SOS2 header function. So resource C10 gives you that function to write the biquad filter to a C header file. So we'll call that pdif.h in your lab exercise 8 project folder. So ideally, you actually do this. You don't put them in separate places. You don't write that file and then copy it over. Ideally, you have it just write directly to your MATLAB will write directly to the header file that you can then just deploy, just run it. So your project, you have to rebuild it. You rebuild your project. So run the MATLAB script, your first MATLAB script. It'll design the controller, pick your gains. You're going to convert that over all the way into a transfer function that then gets turned into biquad sections, that then gets turned into a C header file. You rebuild your C header or your C program, and you deploy it, and it'll use the new gains in there from your. So like you can go back and forth from MATLAB all the way to the hardware. So pretty cool. That header can be included in your MyRio C program after the definition of the biquad struct. So it's writing a biquad, so you can't read it in until you know what a biquad is. In this way, when you run your C program in Eclipse, you will automatically incorporate the latest version of your compensator design. The level of cool this is hard to I think that it's really easy to not recognize how hard it is to do all of these steps. I think you guys have an idea of it. I'm not saying you don't appreciate how many steps there are involved in it, but to be able to go from a MATLAB theory all the way to the hardware that it's implemented on and have it run, it's a lot that has to go into that. So being able to do that whole process and then get the data back and then turn it into a report at the end, it's beautiful. And I honestly have to say, I don't think that this is something that very many people get exposed to in school. Like most of the time, and not even in the real world either. It's hard to do this, and so there are only specific classes, certain places that do this, and then certain labs at companies that will have all this capability. So it's pretty cool. It's pretty fun to be able to do it. It makes me excited still. So great. So as in lab exercise 7, your second script will load the actual response of the position control system. So this is after you've run it on the hardware. You've dumped the actual response. So in your your interrupt service routine, you save the MATLAB data, right, like you guys have been doing. So that dump that to lab8.mat and pull that out in your second MATLAB script to see what the results look like. So the first MATLAB script is going to design the controller and dump that to a C header file. The second MATLAB script is going to read in the data that came back and compare it to the theoretical prediction for what should happen. Okay? This is a lot. This is a lot there.
Yes.
But I will help you at several steps on this, especially the MATLAB stuff.
So are coefficients gonna remain the same, like B0, B1, B2, and just like stop there, or are we designing something that can, have a much larger transfer function?
I think we're only going to use, even with the filter, I think it ends up being, I can't remember, second or third order. So you might need, I think you might just need 1 or 2 biquads, but it's the same process as before though, where you have to update your previous steps as they go through. But you aren't going to have to change, so notice that in this one, you aren't going to have to use a table to edit your gain values. So the gain values in the previous one were entered into the table and you had to read them. Whereas in this case, the gain values are coming from the header file and you're not touching them at all once they're loaded in.
In this lab 8, we just give the path for
Yeah. Well, so so how you should do it is the C program really should have that header file locally in that project folder, but your MATLAB program should, when it dumps that header file out of it, it should dump it to your C project folder, and you can give it the path to your C project folder, and it'll.
So is it like a MATLAB command to dump the information to Eclipse, or is it an Eclipse command to grab it from MATLAB?
So all you have to do in Eclipse in the C program is just include a header file. In the MATLAB script, you're going to use this SOS2header function.
Yeah.
So it's a MATLAB function that dumps it to a header file. So yeah, it's really, you work in MATLAB to dump it to a header file, and then in C you have to just pull in the header file.
Okay.
So just as you typically would, just include it. So
So after we record data to the MATLAB.8, this data can be used by the second script that we will write.
right, because in the second script you're going to want to compare the result to the theoretical prediction for what it should look like.
In lab 7 we have to do that also, simulate this one.
Yeah. But in Lab 7 you didn't have to write this first script, right? In Lab 7 you didn't have to do a controller gain, you didn't have to dump any controller gain design into a header file. So yeah. In that one it's just a table entered K, P, Ki, and
We have the recorded data and plot it with the theoretical one.
exactly. Yeah. No problem. I know there's a lot of steps to it. I know. I am yeah. I'm aware that there's a lot involved in getting this to work. So I've been happy with your guys' progress. And I know it's been kind of rough at times, especially with the hardware. Stupid connectors. Ugh. I'm so frustrated with those connectors.
But in fact somehow it is our code that is not working fine also.
Yeah, it's so hard when you aren't sure if it's the hardware that's malfunctioning or if it's your software. Like, then it's just so many possibilities. Yeah. So this program is going to be a lot like your previous ones, right? You're going to have a main thread and you're going to have a timer thread, right, for your interrupt service routine. And as we've been saying, the controller is derived from that header file that you defined in MATLAB. So, describing the main thread for a moment, it performs the following tasks. First, it initializes the table editor. You are going to have a table editor, but it's not going to be changing as many parameters. You're not going to be, it's not going to have 6, I think it's going to have 3 in this case. Initialize the path profile variables as follows. So these are your correspond to your X max, V max, and A max.
So these paths will be a function of time.
Well, these are the max ones, so they aren't functions of time, but yeah. So how you define a segment is you define it as the you define the x displacement, the velocity max, the acceleration max, and then your d is the duration, the time duration that you're going to have that take place over.
You said 10 seconds, it will just go through these paths for 10 seconds.
Yeah, it'll take 10 seconds to ramp it up. Yeah. So it's how long your ramp takes. Okay, so that's something that'll happen in the main thread. Set up the timer IRQ interrupt. So just like before, as in lab exercise 7, register and create the timer thread to catch the timer interrupt. Timer thread will gain access to both the table data and the path profile through pointers in the thread resource. So notice, for instance, seg, which is what we just defined up here, we just had a prototype of up here. We will use to pass that through the thread resource. And number of segments, the ready flag as usual, the table just like before, IRQ context just like before. So most of this is the same, but there are a couple things that are different. The segment is different, and then number of segments, and that's it. Those are the only two things that are different. Call the table editor. Table should contain 3 show values labeled as follows. So the reference position, the actual position, and then what the voltage is that's being given to the amplifier. Yeah.
Why is the number of segments a unsigned integer?
Yeah, it could be an unsigned integer. I guess it.
Number of segments?
Either one would be fine. Yeah. I mean, unsigned integer is important to use in cases where you want to compress down what your how much memory it uses, but yeah, you can always get away with an integer if you want.
Okay.
If you don't mind, yeah. But you're right. Now we ran into that issue, of course, this last time debugging. We tried to put a negative integer in an unsigned integer, and that wasn't good. And it failed so silently. So silent.
Work only one way and the other way doesn't work.
Yeah, worked just fine the one way, and then the other way, it wasn't throwing an error or anything. Compiled just fine, happily. Yeah. When the table editor exits, signal the timer thread to terminate, just like before, and then wait for it to terminate. So main is pretty much the same as it was. Timer thread is going to be very similar too. Calls the interrupt service routine at the beginning of the starting function. Declare convenient names for the table entries from the table pointer and for the ramp segment variables. For example, you could use these, which would allow you to not have to write this gross thing from the thread resource, get the table, and then get the value from the table. Yeah, this would way rather say pref, pact, and you guys did this in the last one too,
Yes.
so you guys are familiar with this. You guys are like very experienced now, ready to take on this last one. Nothing phases you anymore. So the timer thread includes a loop timed by the IRQ, and is terminated only by its ready flag. So it terminates when in main we set the ready flag to false. Before the control loop begins, initialize the analog input-output and set the motor voltage to 0 using AIO write. Set up the encoder counter interface as in exercise 4, or actually exercise 7 too.
So is setting motor voltage 0 before you run it, is that absolutely necessary? I've tried it both ways and I didn't see a difference.
I think it's just safer in case I think you like screw something up, right? Because if it does, like for instance, if you set a value that if you don't set it and then your while loop isn't working, then you're going to be writing whatever you're writing. It's nice to always, so I know I've seen it happen a few times, but when debugging, you end up terminating before you exit it and set it to 0. And when you do that, it just keeps running, right? And if you want to stop it from running, then you just rerun your program. And if you're setting it equal to 0 at the beginning, then it just stops it. It's just kind of like a nice, like in case while you're debugging, there's an issue. It really, like after the first time through the loop, after you've gone through the while loop once, it should be whatever you're setting it to. So it should be fine. But especially for debugging, it's nice to have that just to make sure that it sets it to 0 instead of some other wild value. And yeah, it saves you from hitting the emergency stop on the amplifier. So, okay. Then set up the encoder counter interface like before. Each time through the loop, it should get ready for the next interrupt by waiting for the IRQ to assert, then writing the timer write register and writing true to the timer set time register. So that's the same thing with timing in the loop before. We did the same thing previously. That's why we're glossing now. We're at that point where we can gloss over this stuff. You guys know all this stuff. Then this is new. Call sramps to compute the value of the current reference position, pref. So we'll look a little bit more into sramps and how it works below. Then call the position, POS, function to obtain the position of the motor, p_actual, see below. So this is going to be like our vel function, but for position. So we'll have to revisit that. But instead of finding the difference from the last call, you have to find it from the very first call. So that's the real difference for position. For position versus velocity. Pause versus vel. Pause. Compute the error, or the current error. So your position is telling you the actual position, so p_actual. So pref minus p_actual is your error. Then call Cascade to compute the control value from the current error using the PIDF control filter. And of course, important, limit the computed control value to the range 7.5 to negative 7.5 volts, which you guys have been doing already. Then send the control value to the D to A converter, the C00 using AIO write, just like before, and change the table to reflect the current conditions of the controller. And finally save the results of this BTI for later analysis. So in broad overview, very little is different in this program than the last program. And especially given the fact that SRAMPS is written for you.
Pause is written for you.
Pause is not. You have to write your own pause. It's not super hard though. Copy and paste your val, change like one thing. So, but we'll talk about each of the functions now.
Yes.
So Cascade, same. Don't change anything. And in the last couple labs we used Cascade. In this case, you only need to use one biquad section. Note that, as in lab exercise 6, all calculations should be made in double floating point arithmetic with regard to Cascade. Then pause. Write a pause function to read the encoder counter and return the displacement as a double in units of BDI encoder counts relative to the first position read. So you gotta figure out how to assign it the first time it comes through, and keep that one around to compare to later. So that's like the trickiest part, is to figure out how to know which is the first time it's called. Okay. SRAMPS. The C function SRAMPS, given in resource C9, returns the current input reference position pref. The function accepts an input array of structures, each describing a separate displacement ramp segment. Remember that a segment is defined as like the final position, the max velocity, max acceleration, and the duration that the ramp should take. Called once each cycle. So let's see. Function accepts an input array of structures, each describing a separate displacement ramp segment, seg. Called once each cycle of the control loop, SRAMP steps through the segments, then repeats the complete path indefinitely. So it goes through the segments, and then it'll just keep going through the segments. So it's an infinite loop until you send an you change the whatever the Boolean is that comes to the thread resource to false in main. So we do that by hitting backspace on the keypad, or you could do it with an interrupt that comes from a digital in. Yeah, there you go. Stop. That would be a good project. I would. That's an A project right there. Voice recognition. Yeah. Okay. We will initialize the path array in main. Then pass the array and the number of segments to the timer thread through the thread resource described in the main thread section. First, define the new segment data type seg. So this is actually the same as above, but it's a little bit more detailed. So position in revolutions, velocity limit, acceleration limit, and I forget what the units are on those. Revolutions per second squared and revolutions per second is what those units are. And then dwell time in seconds. So then, to test the position control system, initialize an array of mySegs of type seg as follows. So mySegments is going to be an array of segments. So that's why it's type seg. We are going to say our displacement values are going to be 10.125, 20.25, etc. So these are the positions, and then we've got our velocity maxes, our A maxes, and then our dwell times. Oh, these are dwell times, I should say. I think I said the duration of the ramps, but they're actually dwell times. So go to the next one and stay there. That's right. You can't specify all of them independently. So if you specify Vmax and Amax and displacement, that fully defines your ramp. So you can't also specify duration. So it's dwell time at the end. So D is dwell time.
Like go
Previous
to
one.
position 1, stay there for 5 seconds, and then go to position 2, something like this.
Yes. So the dwell time, the way that this example is written is it'll stay 1 second everywhere. Yeah.
So it says positions in units of revolutions?
Yeah.
Okay. So
So-
not degrees, not radians, just...
In revolution. So 10, it'll do 10 and then 1/8 revolutions first. And then it'll do 20.25 revolutions next. And then, yeah. So it's going to go around multiple times.
Oh, and then so if it gets to like, so it starts from 0 revolutions, right?
Mm-hmm.
And it goes to 10.125. Then does it do 20 or does it do another 10.125?
So these are all relative to the initial position. So it's doing 10.125, and then it's doing another 10.125, and it's doing a third 10.125. It's doing a fourth 10.125 to get to 40.5, and then it's going to go back down to 30.625. So it's essentially it's going one direction. It says like spinning, say, clockwise 10 times, and then it'll go another 10 times, and then it'll go another 10 times, and then once it gets to 40 times, 40.5 times around clockwise, it's going to turn around and come back to 30 times around, and then come back to 20, and then back to 10, and then back to 0. That's what this, like, it's like, so it's like a triangle, right? Stepped. It's like a ziggurat. I don't know. Isn't that what those are? It's a thing. Okay. Good. Notice that mySegs consists of 4 increasing ramps, followed by 4 decreasing ramps. All the segments are subjected to the same velocity and acceleration limits, and all dwell for 1 second before proceeding to the next segment. You should declare the prototype of S-ramps to be this. So it accepts arguments, segments in the array, number of segments. So segments array is going to be your mySegs, yeah, your array you just defined. Number of segments, which is, I guess, 8 in this case. Current segment index. So you're going to call this repeatedly. So you call this every time through. So you are going to have to tell it what is the current segment index that you're on right now, and what's the current time index that you're on right now. Sample period T, and your next reference position. So this is what SRAMS is expecting.
Is T this time the duration of the SRAM that they use?
So this T is the sample period. So this is our 0.0005 seconds.
So it is like BTI over 1000.
Yeah. But we're not using the table this time
Yes.
to enter the BTI. I mean, you could, but that's not asked of you in this one?
This is the separate value. But we can use it with the timeout value of the timer thread, like it is 5 milliseconds. Milliseconds.
Well, you're gonna want to. So whatever you do with your BTI, you want to make sure that you keep it the same in the MATLAB script that generates your controller, because it's assuming it's going to be 0.5 milliseconds. So you just have to make sure that it's the same here. Otherwise, it will be weird, and it won't work very well. Yeah. Okay, so at the end of the last segment, sramps returns the total number of time steps in all of the segments. It returns 0 otherwise. Typical call to sramps might be nsamp equals sramps and then all of this stuff. When sramps is called for the first time, set dereferenced I time to -1 and dereferenced I seg to -1 to initialize its operation. So that it will be properly initialized. When it does the increment, it'll go to 0, which is what you want. Okay, saving the responses. This is the same as it was in the previous ones too. So the data can be conveniently saved by defining data arrays in the ISR for each of the reference position, actual position, and the torque. Then an auto-incremented index variable is used to store the data in the arrays during each BTI. Increment the index as needed, stopping when it reaches the length of the arrays. A convenient length would be 4,000 points each. After the main loop terminates, but while still in the timer thread, write the results to lab8.mat. The results should include your name as a string, the reference position array in radians, cast to double, the current position array in radians, the torque array in Newton meters, the PID F array, cast to double, and the BTI length in seconds. Then use the same methods as the previous exercises to bring the lab8.mat file to MATLAB, and then you can do your second MATLAB script, which is the plotting of things and comparing with theory. So, procedures to test and debug your program. The MATLAB analysis is kind of one of the big aspects of this, I guess. So, load the experimental results from lab8.mat. Define a discrete version of the motor load plant transfer function from lab exercise 7. Consider using C2D. Form the discrete controller from the values of PIDF array in lab8.mat. So then you'll have your discrete system ready for simulation. Form the closed loop system models relating the reference position Pref input to the position P actual and torque outputs. So this is something that requires a little bit of MATLABing here, and I'll try to help you guys with this. So what I'm planning to do with this part is I will help you with the controller design side first, because that's the part that helps you get the controller working. And then as we progress, I want you guys to be asking me questions about, like, so how do I come up with this? And then I will try to do like mini help sessions on that, because I don't want to do it all for you guys. I want you guys to kind of struggle with it, but I want to help you guys too, because I know that you're not all at the same level of understanding of MATLAB and controls. So, good. In a single MATLAB figure, plot the results in 3 subplots versus time. So as follows. So you're going to want to have the reference position, the theoretical position, and the experimental position all on one plot. So that's going to look like this thing that I was drawing up here, right? Like this. But so say like the black line is reference and the green line is the theoretical prediction. And then we're also going to have data points on here. Probably didn't need that density. But.
Down there, 2 point.
Yeah, but this is what it should look like approximately. Is you should see the ramp, S ramp happen, and you should see the position. The theoretical one prediction should go up there and do its thing, and then the data should be pretty close. Okay, so super fun. And then the next plot would be the experimental error. So the reference minus the experimental position, and the theoretical error, the reference minus the theoretical position. So those should also be pretty close, but they will probably be slightly different, right? And finally, the theoretical and experimental torque. So
is SRAMP giving us the torque?
No. So the torque is essentially a theoretical torque based on the voltage. The relationship between your voltage reference that you, or the actual voltage, the VDA out one, the actual voltage that you put out, that's proportional via the gain of the amplifier to the current, and the current is proportional to the torque via the motor constant, right? So at some point, I think we drew this where it was like, here comes in the voltage. This comes from your like VDA out or whatever we've been calling it. And it goes through your amplifier, which has some gain. We'll call it Ka. And then that gives out, that puts out a current. It goes through your motor, which has a gain of K M, and that gives you a torque that gets applied to the essentially the mechanical side. So I think we had the model. Yeah, 1 over JS plus B, where this is the inertia of the rotor, the motor's rotor, and plus the inertia of the flywheel.
So we just take the voltage multiplied by the KVI and KT, we get the torque.
Yeah. Did I call this KT?
Yes, KT.
Call it KT, not KM. And did I call this KA for amplifier?
KVI.
KVI. That would have been clutch if I had remembered that, but I didn't. And then B is the damping. So this is like the bearing damping. So this is a little bit nicer to work with. Notice that we didn't have to model at all in this the electrical circuit side of the motor, and that's really nice for a couple of reasons. The first reason is that it's just a simpler model. That's nice. But the second is that you don't have to know the electrical properties of the electronic side of the motor. The reason that we're getting away with this magic is that we have this current amplifier. So we have this, it's so-called voltage controlled current amplifier.
Yeah.
And so it's specifying the current it's going to deliver based on the voltage that you put in. which corresponds directly to a torque that you're applying to this mechanical system. It's really nice. So it's saying independent of what the circuit is, what the, for instance, the resistance in the windings is. Regardless of that, this amplifier should be supplying whatever current it says it'll supply up to a certain voltage max. That's why for motor control, people like using these voltage-controlled current amplifiers because it's a little easier to model. But never fear. Remember, we did it the hard way. We didn't use the current amplifier. We just used voltage input to control to model a motor, including the electrical side, at the end of the mechatronics course. At the end of the mechatronics course, we, instead of using this sort of nice voltage-controlled current amplifier, we just had a voltage source that applied to it. And so we had to use the dynamics of the circuit, we had to use the inductance of the winding and all that in our model, which is totally fine. Either way is totally fine. It's just that this way has this nice little aspect to it where it's sort of simpler and we don't have to worry about it.
So inside the amplifier, they have these two characteristics built inside that box.
In this box,
Yeah.
the amplifier box. So in the amplifier box is actually there's an amplifier circuit that's in there that's not like a super complex circuit, but it's a relatively complex circuit that essentially gives you the ability to do plus and minus voltage and have a nice linear response in your output current to the input voltage. I have the filter design if you're interested to see it. I don't have it on me though, but I could look it up. It's a pretty cool. It's a pretty cool box, but it's a pretty common filter. Or it's a pretty common amplifier. So if you get a, I forget. The heart of it is a specific chip that does the. I forget what it is. It's a sort of like a motor driving amplifier chip that's at the heart of it. I can't remember what it is though. I have to look it up. But it's pretty common for driving motors.
Because I read a few articles for our lab 7s. They talk about this also. The system is widely used because it is easy to modify and give the good performance also. Considerable good performance.
Nice. Yeah. Yeah, I mean, doing motor, supplying power to a motor is something that a lot of applications need that. So a lot of times in industrial applications, you're going to see AC stuff, big industrial applications. One of the biggest drawbacks with those is it's relatively hard to do control with those and do closed loop, like even speed control is hard. Position control is like not even worth it. But the amount of struggle that it takes to do automation with AC motors is significant compared to DC motors. So they have like VFDs and stuff, variable frequency drives, for AC, controlling AC motors, but position control, at least you're gonna want to do DC. But AC stuff, a lot of times the existing thing that was there that only had one speed is an AC motor, and then trying to retro control it is hard. You can use these VFDs, which is like your only real good way to go
Yeah.
with it. Yeah, so there's a whole lot there, but when you're designing it from the get-go to be controlled, like especially if it's position controlled and DC motor, current amplifiers the easiest with a DC motor, and then you can just boom go right to this process essentially. There are things that can be done with just about anything, but it just becomes harder. So ideally, you don't have to retrofit everything and make it work. But sometimes budgets, you know. Okay, which is actually why we have a voltage-controlled voltage amplifier, and that was our original thing, because budgets. But this other method is, I decided to just bite the bullet and ask for more money for the amplifiers, so, because the amplifiers are really nice. Okay, any questions on this before we do it?
Still, this the way we can model this in Lab 7, the modeling of this
Mm-hmm.
closed loop system in MATLAB.
Yeah. Mm-hmm.
How are we going to do that?
So I can talk a little bit about that.
Yes.
See, I'm gonna stop this lecture though, because it's kind of getting long.